we're still looking at probabilities because it's important to be able to gauge confidence in a measurement or to make predictions about behavior in the future. Now we've looked at probability functions for discrete variables, which are called probability mass functions, and now we're going to look at these probability functions for continuous variables. And it's called a probability density function. The definitions are analogous, but instead of using summations, we have integrals. For a discrete variable, the sum of all the probabilities, or the sum of the probabilities for all the different possible values, is 1. And for a continuous variable, the integral of the probabilities for all the values is 1. And again, with the mean, we have summation and for discrete variables and an integral for continuous variables. The same thing for variance, which is the standard deviation squared. For a lot of cases, it's been found that for a lot of cases, if we're taking measurements and there's random error sources, then those random errors will follow what's called a normal distribution or a Gaussian distribution, and that's shown here. So the errors are going to be centered around a mean value. This plot shows the probability of having different values for the errors, or probability of having different values. You can see the highest probability is at the mean, and then probabilities taper off according to this normal distribution. There are two parameters that dictate the shape of this distribution. First is the mean, mu, and that locates the central tendency. And the second parameter is the standard deviation sigma, which governs how flat this curve is, the dispersion. For this plot shows 4 different values of sigma, shows the normal distribution for 4 different values of sigma with a mean of 2. You can see that for the smallest value of sigma, we have the sharpest peak. That means that smaller standard deviation will give you more values around or close to the mean. And then when we have a big standard deviation, our values are going to be spread out more around the mean. Again, the integral of this curve is going to be 1, no matter what the value for the standard deviation is. So that's why we have a more narrow but higher peak for smaller standard deviations. If we want to find the probability of getting a certain range of values, so if we want to find the likelihood of our variable x being between x1 and x2, then we need to integrate this function between x1 and x2. So here's the integral of that function. Now this integral cannot be evaluated analytically, so it's done numerically. And for a certain system, we'll have a given value of mean and standard deviation, and we could evaluate this numerically for all these different systems that we have, different values of mu and sigma. But what's done is a variable substitution so that we can have a general case. And then whenever we have our specific systems, our specific variables, and standard deviations and means, then we'll just change those into this general variable and use an integral table to get our values for the probabilities. And we'll look at this in a little bit of detail more later. The variable that we're introducing is called eta, and it's defined here by this quotient, which you can see in the function for the normal distribution. Just rearranging this, we want to be able to substitute eta into this expression, so we need to get x in terms of eta and dx in terms of d eta. So we have dx is sigma times d eta. And now we can rewrite this integral in terms of eta. So now we're finding the probability that eta is going to be between eta 1 and eta 2, and it's given by this integral. And here is the normal distribution function rewritten in terms of the variable eta, and it's generalized, so the mean is 0 and the standard deviation is 1. So here's the normal distribution function for a variable eta with mean, mu, and standard deviation of 1. Now, we're going to look at graphically what this means. Here's our normal distribution function, f of eta, and the hatched area is the probability of the value of eta being between eta 1 and eta 2. The eta 1 didn't come through, but anyway, this lower limit is eta 1 and eta 2. And again, this is the integral here. So if we want to find the probability of getting eta values between eta 1 and eta 2, we would compute this integral. And since that integral can't be computed analytically, it's done in a table, and then we can look up the values for the integral from that table. Since this is an unbiased distribution, it means it's symmetrical. So it's symmetrical around the mean. The area here between 0 and eta is the same as the area from negative eta to 0. So this table just gives you areas under the curve from 0 to eta. And if you wanted to find from negative eta to eta, you would just multiply that area by 2. Or if you wanted to find the probability of values from negative eta to 0, you could still use the table from values from 0 to eta because of the symmetry. So the way this table works is if you're given this first column corresponds to the most significant digit of eta, and we have a table for values or integrals for values of eta with 2 decimal places. This is the first significant digit, and then the other columns are the second decimal place. Say we wanted to find the probability of eta values between 0 and 0.05. Well, the first digit is 0 and the second digit is 5. So the probability of getting values in that range is 0.0199. That's the area under the curve, assuming a Gaussian distribution. This slide we're going to try to do 2 things, so hopefully they'll both come through. We're going to look at how to use the integral table and also consider this concept of odds instead of probabilities. We're given here different values of deviation and the odds that the result is going to be within that range, or the variable is going to be within that range. So for 0.67 standard deviations, plus or minus 0.67 standard deviations away from the mean, we have 1-to-1 odds. For 1 standard deviation away from the mean, there's 2.15 to 1 odds that the value is going to be within that range. For 2 standard deviations, plus or minus 2 standard deviations away from the mean, there are 21 to 1 odds that the value is going to be within that range. So a quick thought on these odds. What this means is that if we had 22 chances, 21 plus 1 chances, then 21 of those times the value is going to be within this range. So picture a pie that has 21 plus 1 slices. Well, 21 of those is going to be within this range, and 1 of them is not going to be within the range. So 21 of those is going to be success, and 1 of them is going to be a failure. So this is a pretty high percentage. Here, this is 50-50. This is like 95%. And then if you go to this, you'd have a pie with 370 slices, and 369 of those would represent the likelihood that you would be within this range. Anyway, first of all, let's say we don't know the range of values that have a 50-50 chance. So we want to calculate that range. So first of all, we want to change these odds to a probability, which is what the integral table gives us. So again, we have 1 slice out of a pie made up of 2 slices, and that's 0.5. So we have 0.5 probability. Now, our integral table is in terms of eta, which again is x minus mu divided by sigma. So we're looking for values within a range from the mean. So we're talking about values, x values that are away from the mean mu by a certain deviation. Anyway, let's just say we want to find the eta values that correspond to a 50-50 chance. And once we had that value of eta, we can find the distance from the mean mu by multiplying through by sigma. So we want to find what portion of sigma gives you a 50-50 chance. Or in other words, what value for eta will give you this area. So our area is 0.25 because we're looking for plus or minus variations around the mean, and so that would be twice this area. So we want to find what value for eta gives us an integral of 0.25. Here is our table, and we want to find 0.25 in that table. So the integral value is between these two. So that means that eta is between 0.67 and 0.68. We'll use linear interpolation to find a close estimate for the value eta, and we come up with 0.6745. So that's how we use the integral table if we know the probability that we're interested in. On the other hand, we can also use the integral table to say if we know the range of values, then we want to find the probability of something being in that range, and that's what we'll do with this example. So here we're saying what are the odds, again not probability, but what are the odds that our value is going to be within one standard deviation. We see here that this means that eta is 1, so we're saying that one standard deviation means that our values x and our original variable is going to be, or will range from mu minus sigma to mu plus sigma. So we can just substitute in mu plus sigma into this equation and we end up with sigma over sigma, which tells us that eta equals 1 for that case. So if x equals mu plus sigma, then eta equals 1. So we want to find the probability of having values between eta equals -1 and eta equals 1. Using our lookup or our integral table, if eta is 1.00, then the area under the curve from 0 to eta is 0.3413. And since we're interested in negative eta to eta, then we'll multiply that by 2. So that's the probability of having values within that range, and if we want to convert this to odds, then that's the same as the ratio c over c plus 1. So the percentage of the pie, where there are c plus 1 slices. So 2.15 to 1 odds that values will be between, or be within plus or minus 1 standard deviation of the mean. Some examples will help to illustrate how this is useful in engineering applications. But for now, we want to just remember that the normal distribution is one probability density function that is useful in engineering, and in order to find probabilities of values within ranges, probabilities of having values in a certain range, we integrate that function. That integration is done numerically, and so we change to this variable eta that's more general. Whenever we have a specific value in our original variable, we can use this equation to change that into terms of eta and then use our integral table to get probabilities.